again. And yeah, so let's talk a little bit about out of distribution or outlier detection. But before I really go into that, let me talk about the journey that led to that question. And for that, yeah, let me ask you a question as well. Which of these organs are perfused? Any suggestion? Perfusion means is blood in there, or isn't there blood there in the moment? So I mean, I hope you all agree it's difficult. Just to give you the answer, so this is it, and you see that we even have one example where the organ is partially perfused. And so it's really difficult for us to tell. At the same time, it's highly clinically relevant because that is a question that surgeons have to answer every day, basically. And so we said, well, we really want to help there. We want to support the clinical stuff in this question. And so the first step in this journey for us was to figure out, well, why is it so hard to tell? And yeah, the answer is basically how we see colors. So we only can see basically 3 colors and make up all the rest. And we said, okay, we probably need more information than that to answer that. And that's where multispectral imaging came into this problem, into our journey, right? So instead of just working with 3 colors, red, green, and blue, we use 8 or even 16 bands of colors to get more information of the spectra. And then maybe use that information in the spectra to get interesting tissue properties, regress interesting tissue properties, and predict then the perfusion of that organ. And we did some first experiments for that, and it really looks promising. I have a short video for that. So we have this multispectral laparoscope, and now we have this laparoscopic surgery, and there's a clamp applied. And you have this region of interest where you see the blood volume fraction, which basically means how much blood is in this region of interest. Now the clamp is applied, and now over time you can see the color going to blue, which means there's basically no more blood in that organ. And we were like, yeah, that's crazy, that's really cool. So can we sell it to a company and be done with it? And of course, it's not so easy, because of course, before we really can go to the clinic, we have to talk about robustness. And robustness for us also means talking about uncertainty. And yeah, so we already did some work in this direction. So the first question we asked ourselves is, going back from the spectrum to the oxygenation by a neural network actually well defined, or can something go wrong there? So because there might be this following example where we have 2 spectra which basically look the same but stem from different oxygenation levels. And well, a standard neural network which does only point estimates, what did it do in that case? Should it predict the mean? Should it predict the median? Something like that? Doesn't really make sense. And so our next step was to say, okay, point estimates aren't good. Let's try to get a posterior probability distribution that really can detect these multimodalities. And so that is the next thing we did. We had this architecture, the so-called invertible neural network architecture, where with the help of a latent space and a spectrum, we can generate basically these posterior distributions and evaluate them and get information about how well posed this inverse problem is. And then we asked again, are we done? Can we now get it and ship it and everything is fine? Because right now, so we have our training distribution, and so for these test samples, yeah, we can basically predict the posteriors. Yeah, but the open question, of course, is how do we deal with outliers? What do we do with out-of-distribution samples? And we looked at the methods that we had so far, and it was just like, well, they perform just as badly as all the other machine learning methods out there on outliers. Namely, they don't perform at all. And so basically what we decided is we want a multi-stage workflow, where here we have the actual regression part, And before that, we want an out-of-distribution or outlier detection task that filters these samples that we can deal with, so that we don't present spurious results. One key requirement, in our opinion, for these out-of-distribution detection algorithms must always be that they are unsupervised. Because we have a very good idea about how our inliers look like, but we have basically no idea how the outliers might look like in the wild, because that distribution is just such a big range. Yeah, and so we had a little bit to look around what algorithms exist, and of course there are quite a few. Also classical ones, not only deep learning ones, but in the end what we decided to pursue for now is an ensemble approach. And let me show you this here in this example. So let's assume the task that we really want to do is classification, and we want to classify these two clusters. And then we can do this with a linear classifier in this case, and actually there are many linear classifiers that solve that problem here. If we now get an outlier, we see in this example that the class prediction varies depending on the linear classifier of the ensemble that we're using. And so the whole idea that we're pursuing is basically that the variance in this class prediction might be predictive for outliers. Yeah, so that is the rounding idea. You can make that a little bit more rigorous in a mathematical sense. And then you call it the widely applicable information criterion, which is given by this formula. Let's quickly take this apart. So first of all, you have to put in the log likelihood of new models, of new spectra in our case. And so you need models that can produce exact log likelihoods. And then the other thing is that you need to aggregate over the trained parameters of this model. So this is an ensemble approach. You really need to train this model multiple times and then compute this variance and this expectation term. To make this a little bit more tangible, I have another example. So let's assume, 1D example of course, that this is our training distribution given by this histogram, and we have fitted 5 models for the likelihood or the distribution of this training data distribution. So what we actually need is the log likelihood, so let me quickly get that. And we see that the variance there is a little bit better visible, so the models don't all just fit the same. And now the idea basically is that when you're in the clusters, so this large mode and the smaller mode, basically all the models agree. And so you have very low variance in this first term, whereas when you're between the modes, and especially in the tail, the models really start to differ. And well, this difference then is picked up in this variance term, and the WAIC value starts exploding. This expectation term here in the back is more or less for normalization purposes. But the idea being overall, if a sample is in distribution, then all the models in the ensemble should agree on the log likelihood, and so the variance should be small. And when we're out of distribution, this variance should be large, because the models can basically do whatever they want. Now the next point is we need some model to compute this log likelihood, and there are quite a few possibilities out there. You can just use a Gaussian mixture model or kernel density estimation, but for higher dimensions and more complex data sets, those fail at some point. So what we decided to use is, again, an invertible neural network, which is a special kind of normalizing flow network. And what we do there basically is we have our training distribution, and this network can transform that distribution into any other distribution that we want, and we want to look that it looks like a normal distribution, standard normal distribution. And because of the special architecture that we have a tractable Jacobi determinant in this network, and with that we have the change of variable formula, and because of that we can compute this log probability exactly. And so this formula, the first part is just the log likelihood of the normal distribution, and the second part is from the change variable formula. And here you see we need the Jacobi determinant to compute this. Yeah, and so we said, okay, invertible nets and WAIC are a good fit. Let's try out and see whether that works. And yeah, that's what we did and what we're still doing. And we have yeah, some preliminary results on that. So first, we basically did an in silico validation. We have a simulation framework for spectra, where we can produce different spectra belonging to different tissue properties. And what we did is we separated the spectra that we produced into two different sets. First, the training set, and then what we call the superset, differing mainly, well, in the support. And the idea, of course, being that so evaluating on the superset, all the spectra lying here should hopefully be classified as inliers, and everything in the tail as outliers. And that is basically exactly what happened. And we were like, okay, nice, it works on simulated data. So let's see what happens if we try it on real data. And for that, we evaluated on porcine organ data. Again, I have to talk about the simulation framework. So basically, we have to simulate all the chromophores that we have in these organs. And our simulation framework can handle quite a lot of those, but not all. For example, it cannot handle bilirubin, which is in bile, and therefore in the gallbladder. And so gallbladder is an organ that our framework and our models cannot handle. And so our outlier classifier should be able to detect that and say, hey, no, we cannot work on that. Please point the laparoscope somewhere else. Yeah, and so here are basically the results. So we trained on the simulated spectra, evaluated on the porcine organs. So this is the WAIC histogram for the simulated test spectra. This is the histogram for good pig organs, so organs that we should be able to deal with. And here are the ones for the gallbladder, which we are not able to deal with. And there are two key observations here. First of all, even though our simulation framework should be able to cover the green organs, WAIC still thinks that they are very different. So there still seems to be quite the domain gap between our simulation domain and yeah, the good organs that we would like to cover. The good news is the gallbladder has still higher WAIC values, and we can definitely separate between the two, and that's promising. Yeah. And then we also did one last experiment as a sanity check, because also for our framework, of course, the lighting conditions are important, because of course the light source influences how the spectrum looks like, and sometimes it happens during surgery that the lighting will change, and we were looking at can we pick up on that. And for that, we took a healthy human volunteer, namely me, and took a laparoscope and took laparoscopic images of my lip and changed the lighting, yeah, at some point. And just had a look whether we were able to pick that up. And yeah, you see it's very stable. Although there is quite some movement, it's also nice. So then we switch the light, and yeah, also there, it stabilizes very quickly and is clearly separated. Yeah, and that is what we're working on right now. We try to refine it and make it very robust and take this as our next step on the journey from bench to bedside for our question. And that is actually all I wanted to say today. Thank you very much.
Thank you. So are there any questions for the speaker?
Thanks very much for your talk. So I don't know how related you think the problems of adversarial examples are for things like this, but because you're taking an ensemble approach, I think it's been shown that, especially because you're training the same model architecture, they might be vulnerable to the same sort of adversaries. So are you worried about the theoretical guarantees that the variance in your ensemble will pick up something when it comes to the bedside?
Worried, definitely, but I don't have any answers. No, but you're completely right. We don't have any theoretical guarantees at the moment. So we didn't come up with using WAIC in deep learning. There was another paper playing around a little bit, and there empirically on some data sets they showed that it's better or more robust than just using the log likelihood as an outlier score. But yeah, no guarantees at the moment, and I'm pretty sure you can find adversarial examples.
My question is about in distribution. If you have you have the Jacobian distribution, and if you how good is your method in detecting these as in distribution, or how hard is it to actually find all your in distribution samples really in the distribution, not that they are detected as out of distribution?
I mean, that is a question that I actually haven't really answered during the talk, right? So if I maybe go one slide back. So basically the question is where do I threshold, right? Because I have this test WAIC distribution, and the WAIC is just a score. To decide if something is in or out of distribution is still something I have to do. And that isn't easy. I would say it's also, rather application specific. So I think one way to go about it is actually enforcing like a quantile or percentile threshold on some test set that you have, and say, well, we want at least 99% of those test data to be classified as in distribution, and go from there. But I don't know about any elegant way to solve this.
Thank you. I think we have time for one more question, if there is one. Yes. You want the microphone?
Oh, sorry. Yeah, thanks for the talk. Just a quick question. So you said that the outlier you showed in this linear classification case was kind of close to the decision boundary.
Yeah.
But then if you go somewhere far away, wouldn't you expect the classifiers to agree between themselves?
Yeah, I mean, this was a really simple example with this linear classifiers. I mean, of course, you can find outliers in this example. I mean, when they are just far to the left, I mean, all will agree, and it won't work in that setting. Yeah, totally. I mean, this example is just too simplistic.
Okay, thanks.
Yeah.
Okay, so let's thank the speaker again. So let's move on to the last part.